3.6 Graphing rational functions. A rational function is a quotient or ratio of two polynomials, for example, x plus 1 divided by the quadratic function x squared minus 3x minus 4, where that denominator, x squared minus 3x minus 4, cannot be equal to 0. So, since this is the example, the rule is the denominator. So to find the domain, we need to find what values of that quadratic give us 0 in the denominator. So we need to factor. So what multiplies to give you negative 4 that adds to give you negative 3, negative 4, and positive 1. So since these can't equal 0, we do our little linear problem, set them equal to 0. So that we know that x can't equal positive 4 and x can't equal negative 1. So what does this mean for our domain? Well, that means it's all real numbers except negative 1 and 4. So in interval notation, we start at negative infinity all the way to negative 1, but we have a parenthesis because it can't equal that. So that's where we start again with a parenthesis, to 4 with a parenthesis, and then we finish up with 4 to infinity. Again, 4 has a parenthesis. So this is how we write it in interval notation, all real numbers except negative 1 and positive 4. Now, there's a line that a curve approaches, but it doesn't reach, and it's called an asymptote. Now, it's also important to mention that it's going to be a vertical asymptote. Now, it's in parentheses because we don't just have vertical asymptotes, we also have horizontal asymptotes. But horizontal asymptotes have a little bit different characteristics. So when I say it does not reach it, I'm referring to a vertical asymptote. So when we identify vertical asymptotes, then essentially a vertical asymptote occurs when x equals b, when x minus b is a factor of the denominator only. So let's look at this example. Well, we need to factor the numerator and the denominator. So our numerator factored, if we did it by grouping, so we have to do 2 times negative 2, which is negative 4. So what multiplies to give me negative 4 that adds to give me 3? It's going to be positive 4 and negative 1. So I break that up into 2x squared plus 4x plus negative x minus 2. And then we group them and pull out a GCF. So we have x plus 2 and 2x minus 1 as the factors of our numerator. And then for the denominator, this factors into x minus 3 and x plus 2. Okay, so why do we do this? Well, I'm going to actually work over here on this side. So I'm going to rewrite it. I have x plus 2 times 2x minus 1 all over x minus 3 and x plus 2. So we factor the numerator and the denominator to see if anything can be simplified. And it actually can. So when something can be crossed out, like our x plus 2's, since they're being multiplied, they can be crossed out. So when we can cross it out, it actually doesn't mean we have a vertical asymptote. It's not a vertical asymptote because it's actually a hole. So if we were to graph, we'd have a continuous line, and then at that value, we would have a hole, and it would keep going. So it would actually be a discontinuous graph. So our hole is actually at x equals negative 2 because that's the value when I have x plus 2 as a factor. Okay, so where does vertical asymptote come into play? Well, vertical asymptote is after you cross things out, if you can even do that, and in this case we can, whatever is left over only on the denominator is a vertical asymptote. So we have a vertical asymptote at x equals 3. So you can notice here on this graph, we get really close to it, but we don't touch it. So there's our vertical asymptote. So essentially what we're saying is we have to identify that the denominator can't equal 0. So what are my two numbers that give me 0 in the denominator? And since we factored it over here, I know there's something going on at x equals 3 and x equals negative 2. But then you have to go one step further and say what? What's happening? Well, there's a hole at x minus 2 because we can cross it off, and then there's a vertical asymptote. I'm going to abbreviate that. A vertical asymptote at x equals 3 because it's left over on the denominator. Now, this factor up here is totally fine. We just factor the numerator to see if we can cancel things out. But if it's left over in the numerator, that's okay because we can get 0 in the numerator. It would just make the whole thing equal to 0. Okay, let's look at two more examples. So our first step for B is to factor the denominator because, well, the numerator is already in factored form. So to get negative 4 and add to 3, we get x plus 4 and x minus 1. And so I'm just going to rewrite the numerator. So nothing crosses out. That's the first thing we look for. Nothing crosses out. So what that means is since we notice that x cannot equal negative 4 and positive 1, it's because they are both vertical asymptotes. So there's no limit to how many you can have and what it is. So you might have a hole, you might not. You might have a vertical asymptote, you might not. So we actually have a vertical asymptotes at x equals 4 and at x equals 1. So I also like to say that vertical asymptotes and holes are the why we have a domain restriction. So other than the fact that we can't have 0 in the denominator, graphically, why? Well, because they're either a hole or they're either a vertical asymptote. So over here, it's beautifully in factored form. So the first thing we do is see if we can cross something out, which we can. So what does that mean? Since I physically cross it off, it means I have a hole at the value x equals negative 2. So what do I care about next? I care about what's left over on the denominator. Well, so that means that I have a vertical asymptote at x equals negative 3. So like I said before, we also have horizontal asymptotes, and they need to be considered as well. Now, vertical asymptotes and holes kind of go together. You have to do the same things and just identify, okay, do I cross it off or is it left over? But horizontal asymptotes have their own set of rules. So you have 3 options. So what you first need to do is make sure that you focus on the highest degree of the polynomial. So you want the numerator and the denominator in standard form because we're going to look at the highest degree of the numerator and the denominator. So if the highest degree is in the denominator, so between the two, the higher degrees in the denominator, then we automatically have a horizontal asymptote at y equals 0, which is the x-axis. So if the highest degree is in the numerator, so let's say we have, x to the 6th and then x to the 5th, this would mean we don't have one at all. Well, what happens then? If you look down here at this case, you actually are given a slant asymptote. So if that happens, it's because there's a slant. And if I took one step further to show you an example, this would be like if I had x to the 3rd and x to the 5th as my highest degrees. Again, I could have like a 2 in front, I could have a plus x squared, all that good stuff, but this is an example when you have a horizontal asymptote at 0. Now, it's also important too on this example, again, I'm talking about the first one. Notice that this middle curve goes through it. Well, on the very first page, I had you specify the fact that you cannot cross a vertical asymptote. Those are walls. Can't cross them ever, ever, ever. But sometimes you will go through a horizontal asymptote. So our last situation is if we had the same degree on the numerator and the denominator. So if I had 2x squared and 5x squared, the degrees are the same on the numerator and denominator. So you actually then have a horizontal asymptote at the leading coefficients. So again, that's why it's so important it's in standard form and that you identify, are they the same or not. If you had 2/4, you'd have to simplify, and you also can have a negative value there too. So it could be any combination. So again, this is where we have a horizontal asymptote at 2/5 for this example down here. Okay, now I want to make sure you understand though that these examples, case 1, 2, and 3, follow these rules. I think I misspoke. This case 3 doesn't have one at 2/5, but let's look at it. If we go to case 1, the highest degree is on the denominator, so we have one at y = 0. No matter what the values are of the numbers, the only time we care about coefficients is for the third case we have. Again, here, since it's greater on the numerator, we have no horizontal asymptote, and again, I talked about that slant. And then in this case, since they're both quadratic here, you have 2/1. So this red dotted line that I actually drew isn't at 2/5. I want to make sure you know that it's at y = 2 for this case down here. Okay, so we're going to look at one example at a time. So we're actually going to look at the first example A. Now, it's important that you may want to use your calculator to help you graph, but all asymptotes and horizontal and vertical asymptotes and all the x and y intercepts need to be labeled and exact. So you really don't need your calculator until the very end. So the first thing I'm going to do for A is factor the denominator. So I will have x over x - 2 times x + 1. Okay, so I'm actually going to go down here to vertical asymptotes because nothing crosses out. So I know that I have a vertical asymptote at x = 2 and x = -1 because those two values make my denominator 0, which I cannot have. So that means for my domain, since x can't be those two numbers, it should be -1. Then I start at -infinity to -1, parentheses. Then I start at -1, and I go to 2, parentheses. Then I start at 2, and I go to +infinity. So I always start at -infinity and end at +infinity. Okay, so now we're going to talk about the horizontal asymptote. So I'm not even going to look at the factored form. I'm going to look at my original right here. Since my degree is greater on the bottom, this means I have a horizontal asymptote at y = 0. So now we need to talk about end behavior. Well, if you can look at the graph now, but as we go to the left, which is x to -infinity, then f of x actually goes towards 0. And as we go to the right, f of x also goes towards 0. And this is because we have a horizontal asymptote. Okay? But it's important to note that this horizontal asymptote gets crossed because it gets crossed at 0, 0, and you'll see when you go to plot points. And remember, that's okay. We can cross a horizontal one. Okay, and the last thing we have here are my x-intercepts, and since it crosses at 0, 0, then we have an x-intercept of x equals 0. So how do you figure this out without looking at the graph? Well, the x-intercepts are actually the zeros. Sorry, my pen's not working. The zeros of the numerator. Now, this is because if we go up top and I put 0 in for x, then when I solve, I'm going to get y equals 0 as well. So anytime I have a 0, like if I had x plus 1 up top here, then my x-intercept would be -1. Okay? And then the last thing that we can't see here, so let's look at that next page, are your y-intercepts. So we have a y-intercept again at 0, 0 because that's where it crosses the x, so it's the same. So now we're going to graph. So since you have everything in front of you, I'm just going to graph. And the first thing I'm going to do is graph my horizontal and vertical asymptotes. So I have a vertical asymptote at x equals -1. And I have one at x equals 2. And I have a horizontal one at y equals 0. So now what you do is the only thing that we can plot right now is 0, 0 because we know that with our x and our y intercepts, and that's the only time we have an x and a y, is look at your table and plot. So when you do that, you're going to get points that are, and you have to estimate the best you can. So you might only get like ones that look like this, but looking at the graph, you know that it gets really close to 0 and it doesn't touch. And then over here on the right side, I have 2, I can identify 2, and then again, if not, it's just, if I kept going, then I'd get really, really small decimal points. So estimate the best you can while looking at your table. So now for the inside, we actually have it look like this, and it like kind of does that S curve through. But again, it never crosses a vertical asymptote. So this is what our graph looks like. So from this graph, it's important that we identify the range. Since we cross through that horizontal asymptote, we actually have a range of all real numbers, or you can write -infinity to +infinity, whichever one you want. Okay, so let's go back up and do that second problem. Okay, so first step, factor the numerator and the denominator. And when I do that, I'm gonna let you guys do that on your own. But when I do that, I get 2x minus 1 and x minus 1 over x plus 3 and x minus 3. So nothing cancels out, but what we know right now is that we have a domain that x can't be positive or -3. So -infinity to -3. -3 to +3. And then +3 to infinity. Well, why can't it be positive and -3? Because that's where I have 2 vertical asymptotes. Then, going to standard form, looking back at the standard form, we need to look at our horizontal asymptote, and since they're both quadratics, so that means that we take the coefficients in front, which is 2 over 1, so we have one at y equals 2. But again, it's important to note, just like before, if I plugged in a value, I actually get one. It crosses at 5, 2. So how do you know this without looking at the calculator? Well, if I have a horizontal asymptote at 2, then that means y equals 2. So I could set this whole original function equal to 2. So I have 2 equals 2x squared minus 4x plus 2 over x squared minus 9. So if I multiply both sides by x squared minus 9, I would get 2x squared minus 4x plus 2 equal to 2x squared minus 18. And then when you solve, you get negative 4x equals 20, and then you get x equal to 5. So it's just pretty much setting it equal to y and then solving for x, or vice versa. So you can look in your calculator and you can see that it will cross the horizontal asymptote, but again, that's okay. Now, for our end behavior, as we go to the left, the function approaches 2 because we have a horizontal asymptote. And on the other side of things, as we go to the right, the function also approaches our horizontal asymptote at 2. So we have only one x-intercept because we have multiplicity. If you notice up top, we have x minus 1 and x minus 1. So we have x equals 1, and then you could say with a multiplicity of 2. And now we're going to do the y-intercept. Oh, and I wanted to point out, I found my x-intercepts because, again, I set the numerator equal to 0. So that's why I'm saying multiplicity, because x minus 1 repeated itself on the numerator. So my y-intercept, when I set x equal to 0 and I plug it in, I get negative 2 over 9. Okay, so let's graph. So the first thing I'm going to do is graph my vertical asymptotes. So I have one at negative 3 and positive 3. I have a horizontal asymptote at y equals 2, so it's up here. And the only point that I have currently is my y-intercept, which is like right here. And then I actually have my x-intercept at 1. So when I go to plot the rest of my points, I actually get in the middle, because there's 3 parts to this, I get this funky looking U shape. It kind of looks like a quadratic, but it's not really. There's no symmetry. Over on the left side, I'm actually up in this left top hand corner. So I'm at 1, 2, 3, 4, 5, 6, 1, 2, 3.5. Then 5, we're a little bit above that. And then 4, we're up here, which creates my curve on this side. And again, make sure you're not crossing any asymptotes if it doesn't show it in the calculator. But over in this top right-hand corner, we have a point about right here, and then it crosses. We know it crosses at 5, 2. It crosses there, and it goes down a little bit, but then it actually goes back up. So that's important to note, and the only way you know that is if you look at your graph, because this creates a minimum, like we've talked about in other chapters. So we have a minimum at the point 9, 1.7 repeating. And to find that second trace minimum, which affects our range. So this one's a little bit more difficult with the range. So we actually are going to start at negative infinity because of these arrows down here. But we have a gap right here. So this highest point right here is going to be 0 because I have the point 1, 0. And then we need to start at our minimum. And it's the y value, and it touches it, so 1.77, infinity. So that one's a little tricky. So it is important to look at your graph, but mostly towards the end instead of while you're doing all the other domain, range, vertical, horizontal asymptotes, and end behavior.